Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. So we said that we have two approaches for aggregation of chunks of documents. The first approach was to aggregate the scores, which means that every chunk or every passage, every sentence will have a score, and then we have to aggregate the score. The second approach, and we mentioned two strategies here, or two models, BERT and MaxP. And the second approach is to aggregate the representation of the different passages. First, let me ask you if you have any questions from the first part. I saw a very nice comment from Hera about having a monster here. I think I agree with you that it's like a monster, but we need to control it. And that's why you need to really think how to use it in your domain, in your specific problem. Use it wisely. Any questions? Everything is clear? Yes, no?
I hope.
I hope. Okay. Okay. طيب يعني خليك متفائل يا محمد. Be optimistic.
Unfortunately, the quiz was not that optimistic for me. Like, I think Ramadan had me bad way.
Huh?
It just seems that machine learning topics have been always over my head, so it's always hard for me to keep up with them.
Okay. طيب, if there's no questions, then we'll move forward. Now we'll talk about representation aggregation, as I said. So it's scores versus embeddings. Well, that's what we mean by representation, right? We represent the each passage, we get an embeddings for it, right? So instead of using these embeddings and getting a score from it and then aggregating the scores, here we can aggregate the embeddings of different passages and then get one score from the aggregated embeddings. Okay. So there are two methods actually in the survey or in the book that we are covering now. One that aggregate the embeddings for individual terms, and another which aggregates the representation of passages. Okay, and the second one is the one that we will cover today, inshallah. The first one is called CIDR. This one is we will not cover, and we'll cover the other one, which is parade. So what is parade? The idea of parade is simple. We also chunk the document into passages, and we will say exactly how, but let's assume that we have passages now. We pass it to BERT. BERT will give us the embedding, which is the CLS embedding for the entire passage. We will pass this into a module that will aggregate these embeddings and give us one score. Okay, so this is different from the previous two approaches, right? Because in the previous two approaches, here we had a score from the fully connected layer, right? We had a classifier, so we added a classifier on top of BERT that will give us a relevance probability, right? That was in the score aggregation. In the representation aggregation, we don't get a score. We take the embeddings, we aggregate the embeddings somehow, as we would see, and then from that aggregation, we learn a model to give us a score. Now the score will be for the document, not for individual passages. Okay, so this is parade. Now, how to? This is of course the high-level overview of parade. How do we split the passages? Parade splits the long text into passages and then do the aggregation on the CLS. The passages are fixed number of fixed length. And for example, it takes 30 passages only, maximum, and with fixed length. Type. what if the document has less than 30 passages? There will be padding. Okay, we'll add dummy zeros to represent the passages that don't exist. Okay, so that's easy. What if the document is longer than that? Is longer than 30 passages? What they did is that they retain the first and the last passages, and in between they randomly sample from the remaining passages. So if I have, let's say 50 passages in the document, I will keep the number 1 and number 50, and all the passages in between I will sample 28 of them, because I need eventually 30 passages only out of the 50. So I have the first and the last. These are 2, and the remaining 28 will be sampled from the passages in between the first and last, randomly. Okay, and there will be overlap. So it's similar to what we saw in MaxP. So the passages also overlap. Of course, there are here hyperparameters that we need to tune. Okay, so these are hyperparameters: the size and the number, and so on. So this is these are now we will talk about how to aggregate the representations. So the first method is to do average pooling. What do you mean by average pooling? Remember that every passage will have the CLS embedding. So P1 CLS of I, that means that for document I, passage 1, we will have the CLS embeddings for it. Okay. Now this is a vector, and each passage will have a vector. We'll get the average of them. Okay. So that will be the representation of the entire document. So taking the embedding of each passage, average them. That's one variant. Okay, so we have 4 variants actually. Another variant is to take the max pooling. So that's max element-wise maximum. Yani you put the vectors, the embeddings, and then take the maximum at each element of the embeddings. Okay, at each dimension. So that's called max pooling. So that's the max. The other one was average. So average, max. The third one is attention weighted average. So here we will take weighted average of the embeddings. So the final embedding of the document will be a weighted average of the embeddings, and these weights are actually learned. Okay, so we'll have like an attention layer, similar to the attention layer that we saw in the transformer, and so W here is the matrix that represent the attention layer, and the weights eventually will be the softmax on the multiplication of the weight matrix with each embedding. Okay, so in brief, each embedding will be multiplied by a weight matrix that will give us a score, and that score will be normalized by softmax to get the weights. So these weights, you can think of it as attention, but the attention over the embeddings. Okay, and these weights are learned. So that's what we mean by attention weighted average. The fourth one is using the transformer encoder part, 2 layers of the transformer. So you pass the entire concatenated embeddings to the transformer encoder that will produce a CLS embeddings. Give it to another layer, will produce another embedding, and that will be the aggregated representation of the document. So for the last one in particular, this is how it looks like. So we'll take the embedding, the CLS embedding for each passage. Now these are the embeddings for the passages, right? If you remember last time in the previous lecture when we talked about the transformer, we said that the input is a sentence, right? And each term has embeddings, which is the actual input. Here, think of the passages as terms. Okay, so we input to the transformer, so that's a 1 layer, actually 2 layer transformer. the encoder side only. We give the input as the embeddings, not of the terms like the original transformer, but now the embeddings are embeddings of passages. But we will pass them to the transformer. Of course, we will learn a model here, and eventually we will get the CLS of, after the 2 layers of the encoder, we get the CLS embeddings for the input, which will be then passed to the classifier, the normal classification layer, to get a final score. Okay, is this clear? So this variant is called parade transformer. So we have 4 variants. The average, so we'll take just the average of the embeddings. Of course, every aggregation will go to a classification layer, which is something like this, right? We'll go to classification layer, and that classification layer will give us a score. So the 4 variants are average, maximum, those are straightforward. The third one was the attention weighted, so we will learn a weight matrix to give the a weighted average of these embeddings. The fourth one is using a using a transformer model to learn embeddings for the document, given the embeddings for individual passages. Any questions? Is the idea clear here?
Doctor.
Okay.
Doctor, you said use a transformer, yes, the encoder. So that means it's BERT. Okay, if he used the same number of layers and nodes.
Exactly. Yeah. That's the But these are just two layers only. BERT has 12 or 24.
So mini BERT,
it's like mini BERT, yes. Yes. But that will be learned also. This is not remember, transformer, the original transformer is not pre-trained. You have to train it on the task that you want. Okay, so that will be trained from scratch for this specific task. Okay, so that's not BERT. It looks like BERT because BERT is the encoder side, or the architecture of BERT has the encoder side of the transformer. Okay, but it's not BERT itself. It's not the pre-trained model. Okay, in fact, in this paper, they used they trained the transformer from scratch and also used a pre-trained transformer called T5. We'll not have time to talk about that, but there is a pre-trained transformer like pre-trained, like BERT. BERT is pre-trained transformer also, right? It's pre-trained in a specific 2 tasks that we discussed last time. At least we discussed one of them. T5 is another version like BERT, which is pre-trained also transformer. Okay, so in the paper also they tried T5. They tried to fine-tune T5 to get the embeddings for the document, and they did a comparison. Actually, it was better than using transformer from scratch because it was pre-trained. Did I answer your question, Marina?
Yes, doctor. Thank you.
You're welcome. Yes, Wathiq?
Yes, doctor. I have a question regarding the way of taking the average or choosing the maximum. Choosing the maximum, just taking the maximum vector. If yes, then
yes,
what
maximum element-wise.
Okay, so what is the implicit meaning of taking the maximum?
You mean the intuition?
Yeah.
Usually, max pooling is used in deep networks now, especially in convolutional neural networks, just to get a summary of the previous of the underlying layer. If the layer has a big size, if I want to get and different dimensions, then max pooling is one way to get a summary of or a shorter or a more compact version of what I had from the previous layers. It's kind of an encoding way of different things. If I have a larger input, I want to encode it somehow. One way is use the maximum. Whether it will work the best or not, we'll see in the results. But it is usually done this way. One of the ways that is used to downsize the embeddings that we have.
Okay, but here we are, the maximum the one that we choose is just representation for one passage. So
no. That's why I'm saying element-wise, element-wise, dimension-wise. Let's say that the embedding is 10 dimensions. Okay? Every passage has a vector of 10 values, right?
Yeah.
I will do the maximum per dimension.
Okay.
Because there is no meaning of a maximum of a vector. You cannot say a vector is greater than another vector, right? But you can compare individual values in the same dimension.
Okay, but even so, we don't know what is the meaning of taking the average of this feature.
Yes. It is like the strongest. You can think of it if this is a representation in the latent space or the embedding space. This is the strongest signal. You are getting the strongest signal in each dimension for all passages, just as a representation for the document.
Okay.
Whether it will be effective or not, that's experimental question.
Okay, no, I got it. Thank you, Doctor.
You're welcome. Let's see the results on, again, robust 04. So you see here the 4 variants: average, maximum, attention, and when the name is dropped, then this is the transformer version, because that's the main approach actually that was introduced by Parade. The other 3 were just baselines. So as you see here, the best was the transformer version, which is the most complicated one. It's not very far, but by a good boost. Okay, so here from 0.4 to 0.52 of course, maximum and attention were not very far here, either in title or description. The difference was not much, but average was the worst of them, and the transformer was the best. Okay, so that's among the variants of Parade. Now, if we look at the difference between Parade and BERT or Max-P that we just covered, you will see that Parade was more effective. From 0.4 here, 0.49 here to 0.52 here. Even in the description, also there was some improvement. Okay, but that shows that Parade is actually better than Max-P and BERT, at least on that setup. Okay. And of course, overall, the transformer, as I said, was the best. Okay. Any question on this? So the idea of Parade is to aggregate not the scores, but aggregate the representations, aggregate the embeddings of the individual passages. Okay. In the previous two methods, BERT or Max-P, we get a score that is assigned for each passage separately, and then we aggregate the score. Type. Let me ask you a question. Why do you think Parade is really better than BERT and Max-P? What is the main difference? What is the key idea of Parade over Max-P that might be the reason why we got better results? And why did we get better results here? What is the key property here? Any guess?
I think maybe because here we are just aggregating or merging the implicit meaning that we get from BERT into another layers or encoder. So these 2 layers will manage or understand to try to aggregate the attention we get from the passages.
For the entire document.
Yeah.
Here, here it's like the model sees the entire document together. Okay, in BERT and MaxP, each passage is seen independently, completely independently. Okay, but here it's like we see the entire document, although we don't see the individual words, but we see the embeddings from all passages. Okay, so the context here is better represented. The context is better represented in Parade and of course in similar methods here that aggregate the representation. Okay, did you get the idea? Yes, no?
Yes.
Okay. One yes? Two yeses?
Oh, yes.
Yes.
Okay. Okay, good. Right. Let's move on now. Let's see what how long we have. Okay. I think we will be able to fit that inshallah. Okay. Right. Now we'll switch to what we call multi-stage re-ranking or re-rankers. So what do we mean by that? So far, we assume that we have an inverted index from which or by which we get an initial retrieval results by let's say being 25. Then the top results from here will go through a re-ranker, right, to get the final ranked list. This is using single re-ranker, but theoretically we can use multiple re-rankers. Nothing will prevent us from doing re-ranking to that set, and then re-ranking to the second set, and then re-ranking to the third set, and so on, right? We can do that. We can do that. Type. Should we use the same re-ranker? Of course, doesn't make sense to say the same re-ranker because if we use the same re-ranker, we will get the same results, right? So these re-rankers must be different. In fact, they will be more complex. They should be more complex. Why is that? Because the idea here is that we, as we move, sorry, as we add more re-rankers, the list of the candidates is shortened. Yani for example, here, let's say that we have here 1,000 documents. We do re-ranking, and then we get the top 100. Then we re-rank these top 100 by another re-ranker. Okay, type. Why do we need to do that? We need to do that because there are some re-rankers that are very effective, but complex. They will take more time. So I don't want to apply them on a very long list of documents. I want to apply them only on a short list. Okay, so you can think of it that way. The first re-ranker will be relatively, of course, fast, but it is limited in effectiveness. The second one will be slower, so the efficiency is not that good, but it is more effective. So the ranked list here should be better because I will use more sophisticated features. Okay, yani just the example that even was given in the textbook, I think you can agree with me generally that n-gram features are better than unigram features, right? Yani if I use the bigram, okay, features, two consecutive words always, okay, that will capture some context, right? Better than unigrams, individual words. But of course, bigrams are more complex. Using the bigram features will have much larger space and will take more time, but it will be more effective. Okay, so I want to be wise in using the complex features and the complex models in my retrieval process. I don't want to spend a lot of time on so many documents that most of them are non-relevant. So I might use very fast way to get rid of most of those non-relevant quickly, so that I can focus on the ones that are potentially relevant. So as I move to the right, I will use more complex rankers, which will be less efficient but more effective. Okay, so as you see here, efficiency goes down, which means that it will be slower, but effectiveness goes up. Type, why do I care about efficiency?
This one happened online.
Yes, all of this happens online once we get the query. So we have
since we have less number of documents, it will be affect.
Yeah,
like here I like the first.
That's what we call efficiency effectiveness trade-off. There is a trade-off between effectiveness and efficiency. As we get better results, we will be slower. We need more time. So we will have to study this. We will have to have a way to control this. And this is exactly what the goal of the multi-stage re-ranking. We will apply re-ranking on smaller documents so that overall we can get better results in the same time or with small a penalty of time. Okay, we will see that. But did you get the idea now? We use multi-stage re-ranking to improve effectiveness, with, of course, at the expense of time. Time. Any question about this? Type. We will, inshallah, we will study one example of multi-stage re-ranking, and then we switch to another thing, which would be the last in the lecture and in the course. So the model that we use for multi-stage re-ranking is called BERT. Remember, the first one was mono. Okay, mono 1. Here do 2. So we'll use 2 BERT models for re-ranking. Type. BERT has, as usual, the first stage will get BM25. Actually, this can be seen also as multi-stage, right? We have BM25 to give us an initial list of documents. Then we use mono BERT to re-rank them. Now, after we re-rank the documents using mono BERT, we will use BERT to do a second re-ranking. But the second re-ranking will be, as you see here, will be in a shorter list than the list that mono BERT worked on. Of course, we will talk about the details of BERT next, but that's the idea. We use BM25, then we use mono BERT, then mono BERT, of course, will work on this list, and then we use a shorter list, the top of the ones that mono BERT ranked or re-ranked, and then we re-rank them to produce the final output. If you notice here in that figure, mono BERT work on or takes as an input query and one document. Okay, BERT takes a query and a pair of documents. That's why it's called actually. Okay, not because we use 2 BERT models. Sorry, it's because it takes 2 documents. If you remember, we called this pointwise.
Yes.
Learning to rank. This is now pairwise, as you will see. BERT takes 2 documents and the query and produce a score that is the probability that can be considered to be the probability that the first one is more relevant than the second one. Okay, and that's why it is more complex actually, because it doesn't only assign a score to every document directly, but it compares almost every pair of documents. So if we have n comparison, n usage of BERT here Here we have order of n square usage of BERT, or m square, because m here is the number of documents here, n here is the number of documents here. Okay, so that's a brief overview of DoBERT. Let's look into details. DoBERT takes, it's BERT of course, but it takes in the input, it divides the input into 3 parts. Remember in MonoBERT, we had the query and the document, right? And the passage. And we had a separator between the query and the passage. Here we have 2 passages, still within the 512 tokens, by the way. We are still using BERT. Okay, we are still using BERT, the original BERT. Okay, but we are fine-tuning it in a different way. So the input here will be 2 documents, 2 texts, and 1 query, and there is a separator between the query and the first one, and the first one and the second one. There is a separator here, and there's a separator at the end, of course. Now we will get embeddings for each term, and the CLS will be the embeddings for the entire input, which will be given as usual to a classifier to get the probability. Now, this probability is not the probability of relevance for 1 document, because the input here is 2 documents, right? So it will be the probability that the first one is more relevant than the second one. So that's the input format for DoBERT. It will take query and 2 documents or passages. Still, everything has to be within the 512 tokens.
Doctor, suppose I have like 4 documents, A, B, C, D. First, I'll pass the query with A and B. So
Yes.
this one will give me that A better than B.
Yes.
Then I'll pass the query with C and D. It will give me a C
You will
better
pass
than
the
D.
query. You will pass the query with every pair. We'll get to that, Marina, in the next slide. Okay.
Okay.
Stay tuned. Any question about the format, the input format? Fine.
Excuse me.
Yes, Ahlam, yes.
How
We
can
didn't
I
have
know?
much today, Ahlam. Are you sleeping?
No, I'm with you. How can we know that document 1 is more relevant than document 2? How يعني we will get the CLS.
ما هو احنا we will train. We didn't talk about fine tuning yet, but we will fine tune the model, of course, as we did before, but with pairs of documents. Remember, in pairwise document, in pairwise learning to rank, the training examples were pairs also, right? Exactly here. It's like here also. We will fine tune using pairs of documents.
Okay.
Okay. Right. Now we will. This is just saying that this is the different from the usage of BERT that we saw before, because we have a third part of the document here. Right. Let's talk about training now. So in training, we will have a query. We'll have D1 and we have D2. Right. What are these 2 documents? One of them has to be 1 relevant, and the other has to be non-relevant. If we have just 2 levels, exactly as we did before in pairwise learning to rank. Okay, so that will be the training examples. From all the relevant judgments that we have, every relevant document paired with every non-relevant document, that will be a training example to do BERT. And the classifier will give us now the probability will be the probability that the first document is more relevant than the second document. Now, if this probability is 0, for example, that means that the second one is more relevant, right? If it's 1, then the first one, of course, it won't be 0 and 1, but I mean, these are the 2 extreme values, but we will get a value between 0 and 1. Okay, so is document DI more relevant than document DJ to the query queue? That's the meaning of the probability that we will get from the classifier that takes the CLS embeddings of the entire input. The loss function, very similar to the loss function in MonoBERT, but here, instead of individual documents, here we have pairs, okay? So if you notice here, the summation is always between positive and negative and positive, okay? So when we give positive first, we want the probability to be 1, okay? So log 1 will be 0, so the loss here will be 0. If it is correctly predicted, and if we give the negative first, then we want the probability to be 0, which will the loss in this case will be 0. Okay, is that clear? Any question on this? So this is the training. Is that pre-training or fine-tuning?
Fine-tuning.
Fine-tuning, of course. Okay, fine-tuning.
The same relevant judgment that we fine-tune the sorry, what's the first one? The MonoBERT. It's the same that we are using to fine-tune the BERT.
No. We are not using MonoBERT to fine-tune the BERT.
No. The same relevant judgment, that the same documents and the same data set that we are using there, we are using here. The difference that there, I pass one document, here I pass 2 documents.
Exactly. Yes. Any other questions? Type. This is fine-tuning. What do we do when we do inference now? I want to use the model that is now fine-tuned. If you remember, we start with BM25, okay? Then we take the top, we pass them to MonoBERT. Now MonoBERT gave us this ranked list, okay? So we have the top 3, D1, D2, D3. That's now in inference, okay? In inference, we have 3 documents. So we'll have to try each one with the others. So we will pair them, D1 with D2, D1 with D3, D2 with D1, D2 with D3, D3 with D1, D3 with D2. Every pair here will go over, will be passed to do BERT to get a score. So for example, D1, D2 will give us the P12 score, which will give us the probability that D1 is more relevant than D2. Every pair here will give us a score. Okay, fine. If that's the case, what is remaining? What should we do next?
Re-rank them on the basis of this output.
How?
Which one is more relevant? It will be on the top.
Yes, one way is to just add the probabilities for the corresponding documents. Yeah, for example, S1, which is the score for document 1, will be P12 plus P13 whenever the 1 is the first, okay? And then S2 will be the sum of probabilities whenever 2 is the first, and so on. So that's aggregating from pairs to individual documents, because eventually we need a score for every document, right? So we'll have to aggregate the scores somehow, and this is one way of doing it, is to just add the scores. Now, when we do that, we have S1, S2, S3, and now we can rank the documents, the individual documents, based on these scores. I think Marina had a question about that. I hope that I answered it now.
Yes, I got it, because, and I thought the BERTs we choose like D1, D2, D3, D4. But no, once we have matching document between like D1, D2 with all.
We'll have to, yeah, we have to do it. We'll have to try it with all of the pairs. Okay. Any questions?
Yeah.
Yes, Arthur?
Yes, I have a question regarding preparing the training data here. The non-relevant or the relevant with the non-relevant got 1 as a score. But what about the relevant between each other? Here, if we...
I don't understand your question, Arthur. Are you talking about fine-tuning or inference?
In fine-tuning, we have to prepare the data, right?
Yes, yes. Fine tuning, we have to prepare the data, of course. Yes, we
Okay,
have to
so
prepare every relevant with every non-relevant.
yeah, okay. So at when يعني during the training, if the model predicts or have two relevant document, how we can
We don't do that, Wathaq. If we go back here, all the pairs have one positive and one negative.
oh, so I have to input for the due BERT during the fine tuning. One is the positive and one negative.
Isn't that what we said in pairwise learning to rank?
In pairwise, we mentioned that we have grades, so it's okay.
Yeah, but that's still grades, right? But we have binary here, but you can generalize it. It's the
Okay.
same concept.
Okay, so that's why in inference we just sum up the scores, since
Yes.
we don't have the relevant judgment between two relevant documents.
Of course, in inference, we don't have the labels. Of course, labels are just for training.
Okay.
Okay. Any other questions?
Yes, Doctor.
Yes, Bashir.
Doctor, why we take D1 and D2, then we take D2 and D1?
Very good question. Ideally, we wouldn't have both, right? But the model was trained that way. Yani you have to. It's not, the model is not symmetric. Yani it's not always the case that if you switch the documents you will get the same score, unfortunately. So you have to give it twice, once with D1 at the beginning and once with D2 at the beginning. Did I answer your question, Bashir, or did I answer another question?
Yes, Doctor. Thank you.
Okay, you're welcome. Any other questions? Okay. How much time we still have? Okay. طيب. Okay. Please pay a lot of attention to this figure because it is important to understand it. Okay, and it's not very straightforward. So please focus with me on this. Let me tell you first what is the x-axis and what's the y-axis here. Let's first talk about the cost of mono BERT and the cost of dual BERT in terms of how many times we do we use the BERT. Okay, we will estimate the time by how many times we use BERT for each. Okay, how many queries we pass, or how many examples we pass to BERT in both cases. Right. Let's say that I have from BM25 I got 100 documents. Okay, so mono BERT will be applied on 100 documents. How many? Give me just 1 second. I will be back. Okay, give me 1 second. Okay, assalamu alaikum. So we said that let's say that BM25 gave us 100 documents. Okay, now these 100 documents will be passed to mono BERT. How many calls to BERT we will use to re-rank these 100 documents? Can anyone answer this? With mono BERT,
100.
100. Yes, because I need a score for every document, right? So 100. So 100 calls to BERT. This is what we call here BERT inferences or query. Okay. So in this case, it will be 100. Type. If then I take only the top 10 of them and use do BERT, how many calls to BERT only for do BERT for these 10? Can anyone tell me?
90 or 100? 90.
It's not 100 exactly, because 10 times 9. It's not 10 times. Yeah, 10. It's n times n minus 1. Okay.
Yes.
So if I used only the top 10, then 10 times 9 will be 90. So do BERT will add 90 calls to BERT over the original 100. So the total in this case will be 190 calls. Okay. So this can give us an indication of the time. Yani instead of telling you the actual time, we plot on the x-axis the number of calls to BERT.
Excuse me, Doctor, can you repeat the last one?
Which one?
يعني after we the do BERT will have 90 queries. Yes.
Yes.
90 calls.
Yes. Now
Then
overall we had 100 from mono BERT, then 90 from duo BERT, right?
Okay, for all the system.
But yes, for the
Okay.
entire
Yes.
query now.
Okay.
So the total will be 190, right? And that will be like the time for that query. Okay, so this is I just wanted you to understand this concept, that here we will be counting number of times BERT was called for both mono BERT and duo BERT. Okay, طيب. Now forget about the colored curves and focus only on the gray one. And we said that on the y-axis the number of calls to BERT, on the x-axis the number of calls to BERT, and on the y-axis this is the effectiveness in terms of mean reciprocal rank at 10. Right. If we look at the gray curve, that means that when we used 50, when we re-ranked 50 documents coming from BM25, right? Because mono BERT works on whatever comes from BM25, we got 0.3, maybe 0.38, 0.338, something close to 0.34. But then when we get when we tried mono BERT on deeper ranked list 100, we get better, right? Remember this table when we talked about 50, 100, 1000 and 50, 100? 50,000, and we said that mono BERT is the performance will be increasing until we reach 10,000, and from 10,000 to 50,000 doesn't increase. This is exactly the same, but it's plotted. It was on a table, I think, if I remember correctly. Actually, no. Actually, it was the same curve, but we had this 50,000 after that. Here we cut it at 10,000. Okay, so that curve is exactly the one that we saw before. Okay, for mono BERT. So nothing new here. It's just the x-axis was the number of was in the previous chart that we talked about in the beginning. It was the depth of the ranked list, but actually this is exactly the same like the number of queries to BERT or the number of calls to BERT. Okay, so it's the same exact curve. So that's like the cost of the method. Okay, so done with mono BERT. Any question about mono BERT curve? Okay, fine. Now let's look at the meaning of the brown one. What is the brown one? Brown one means that we applied mono BERT first and then duo BERT. What is the size of the list that was input to mono BERT, and what is the size of the list that was input to duo BERT? Here we assume that we always K1 is 10. K1 is the list for duo BERT. Okay, so for the brown, we always take the top 10 out of mono BERT. And the different points here correspond to different K0 values. K0 is the list that MonoBERT takes. The first one is 50, the second one is 100, the third one is 200, and so on. The same exact numbers that are here, but now the value here is the sum for both MonoBERT plus DuoBERT. So let me explain this for the first 2 points. This point, because it's on the brown curve, it means that K1 is 10. And because it's the first point here, it means that K0 is 50. K0 is 50. Okay, type. In this case, how many calls overall BERT will be called?
140.
140. Why is that, Marina?
It's 50 from MonoBERT and
Yes.
10 times 9 from the for the second for the DuoBERT. So
Very
90
good.
plus 50.
Very good. And that's why it's 140. You see here, it's really very close to 140, right? The value here. Type. For the second one here corresponds to K0 is 100, because that's the second value, and still K1 is 10. Okay, so what is the total number of calls to BERT? 100 MonoBERT. That's 100, right? 100 calls.
190.
And then, yes, and then 10 times 9, which will be 100. 190. So 100 plus 90, 190. That's why we had it here before 200. And so on. So you will always add 90 to whatever the number of MonoBERT calls to BERT. So this one, 200 plus 90, that will be 290. This one is 500 plus 90, so 590, and so on. Okay, so that's the value on the x-axis. But what is the value on the y-axis for this brown curve? It's always the effectiveness. The effectiveness. Type. Now I think now we understand the meaning of both curves. The gray one, which is MonoBERT only, and the brown one, which is DuoBERT overall, using K1 is 10. Type. What do we get from these two curves? We get that when we use DuoBERT, okay, with K1 equals 10, but on 50 and 100 documents, it didn't give us better results, right? Because the performance of actually gave us a better result here compared to this one. So this one is compared to this one, right? Because both use the same MonoBERT. This one is compared to this one. This one is compared to this one. And this one is compared to this one. And this one is compared to this one, and so on. Okay? So
that means we get benefits from DuoBERT after 200?
That means that DuoBERT is giving us improvement, of course, in effectiveness. So that's clear, right? So
after, but like for 50 and 100 didn't. After 200, like after
no,
200.
Actually for 50 it didn't. But for 100 it did.
It's very slight.
Is very slight. Not very slight. The difference between this and that. So this is the difference between this and that, right? I'm sorry that I don't have the pen with me today. So that's the difference, like this one, okay, like this part, okay. And when we go to 200, if we used MonoBERT for 200, still DuoBERT is taking only 10, okay. Then the improvement will be from this one to this one, okay. Type. Now, what is the cost in terms of efficiency? That's on the y-axis. That's the 90 that we mentioned. It's always 90. Okay, 90 calls more. 90 calls more. Okay, but it is giving us better effectiveness. Okay, now we can generalize this on these two curves. The blue one is when K1 is 30. So when K1 is 30, what are the number of calls that we should add to monobert?
$30 times 29.
30 times 29. Very good. 30 times 29. Okay, that's the cost in terms of efficiency, but in terms of effectiveness, you see it is also better. Okay, it is also better. So but better, not too much over K1 equals 10, by the way. I mean, these are corresponding values when monobert with the same monobert, which is 100, but with K1 equals 10 here, with K1 is equal 30 here, and slight improvement. Okay, slight improvement. Here also slight improvement. Here slight improvement. Here slight improvement. Okay, but over monobert, of course, it's a big improvement. Also same here when K1 is 50, it is about a very slight improvement over the previous case. Okay, type. There is one thing that I want you to get here. Let me see. If I want okay, okay, if I have, let's say that I have I can afford 500 calls to BERT. Okay, I can afford 500 calls to BERT. What is the best that I can do? I should use monobert or I should use duobert? If I can afford 500 and only 500.
Duobert, because it has higher efficiency.
Yeah, so it has higher here, right? It has higher what? Higher effectiveness.
Effectiveness.
Yeah. So at that line, the efficiency is the same. The efficiency is the same. But this point is using monobert at what size, what length of BM25 results? 500, right? 500. This one is not 500. It's less than 500. Okay, actually it is total 500, but with K1 with 10. Okay, so K1 is 10. K1 is 10, and actually the monobert has used even less than 200, less than 500. Okay, so what I wanted to say here, maybe it's not very clear, is that sometimes you can reduce the number of documents that monobert will take and play with the number of documents that duobert will take, and you might get even better results doing that. Okay, and you can see this in this figure. This figure, of course, you see now it's not very straightforward. That's why I told you that you need to really focus with me on that. It shows you a trade-off between the cost and the quality. You might increase the cost, but with increasing the cost, you will also increase the quality. Okay, And also, you might have the same quality. Yani if you draw, again, I'm sorry that I don't have my pen, but let's assume that you draw a line from this way. Okay, so these 2 points are almost at the same horizontal line, right? Okay, and let's assume that this horizontal line is like 0.37. So it's the same, this point and this point gives the same exact effectiveness. Same exact effectiveness. Okay, but with much less efficiency for this one. Yani efficiency, I mean much better efficiency, because the cost here is less than the cost here. Okay, so that means that if we let's compare these 2 points, this one and this one. What is this point? What is the size for mono BERT and for duo BERT?
This one is 290 and that one is 1000?
Yes, 290 for a mono BERT. No, I mean not
for duo BERT.
Yeah, we use 200 for mono BERT. Okay,
190
plus نعم
290 because
that's
the K
the
here
total
is 10,
cost.
yeah.
That's the total cost, Marina, but I'm talking about how we can reach this point. We can reach this point by passing 100 documents to mono BERT, then 10 documents to duo BERT, right? Are you with me on that, everyone?
Yes.
100 or 200, doctor, it's the third point.
Yes, sorry, 200, yes, 200. Yes, you are right. So this point, we get it with 200 to pass to mono BERT, then 10 pass to duo BERT. Okay, now let's compare it with this point, this gray point, or the blue point, and they are very, very similar. Let's do the gray point. The gray point here means how many documents passed to mono BERT?
1000.
Almost 1000, yes.
1000, yes, 1000. And yes, 1000 only. Okay, so here we passed 1000 to mono BERT, and here we passed 200 to mono BERT, then 10 to duo BERT, and they got the same effectiveness, and even this one is more efficient. Did you get my point now? That you can optimize by using these 2 parameters, how many documents passed to mono BERT and how many documents passed to duo BERT, to get better performance. Here we got, for this example, we got the same performance but much better efficiency, right? The point here is something like 250 or something. The point here is more than 1000. So it's it's very clear improvement in terms of efficiency with the same effectiveness. We got it by of course playing with the size of the documents going to mono BERT and the size of the documents going to duo BERT. Okay, so these two numbers, K1 and K0, K0 and K1, K0 going to mono BERT and K1 going to duo BERT, allows us to explore the cost quality trade-off much better than mono BERT only. Okay, any question about this? Did you understand the figure and you understand how to understand every point here? Yes, no?
Yes.
From where we can get this the reference for this table, for this graph? The same
This is
survey?
experiments. These are experiments, Marina.
I know, but which survey, which paper?
Oh, did you see the references?
No, I didn't see the beginning. I see one of the survey that you put before for, it's the same?
Yes, it is the survey. I don't have the first page now. It is the same survey that we used in the previous lecture. This is the chapter called multi-stage ranking architectures. This is the chapter that we I don't know if you see it or not. Actually, I don't see it. The chapter that we started last time. Okay, it's the same textbook. Okay. Did I answer your question, Marina?
Yes, thank you, Doctor.
Okay, I think we need to move forward. So takeaways of multi-stage re-ranking. The advantage is that we have more tuning knobs. What are the tuning knobs here? The K0 and K1. These are two numbers that we, by which we can control the trade-off between the effectiveness and efficiency. So more flexibility. But the disadvantage is that we have also more tuning knobs. And the disadvantage here is that this is more complex. As you saw, it's not easy to get it. So more flexibility comes with more complexity. That's the message of this slide. And of course, there are other models than the model that we saw that started to explore this design space. It's actually this survey, as I don't know if you saw my tweet or not, but actually this is the best ever survey paper that I have read in my life. Really very, very well structured, very informative, with clear takeaway messages, and even the description of the methods is really, really clear. I would strongly recommend you, if you are still interested in IR, not just taking the course and you don't want to hear about it after that. If you are really interested, you should definitely read this survey very, very carefully. It is very well written, and it will explain these methods and more, even the methods that we didn't have time to cover in this textbook. Really, really very great job by Jamie and his collaborators. We have 10 minutes. So let me go through this idea of document expansion quickly. If we couldn't finish it, then you should read it. Of course, we don't have any quizzes or exams on that anyway, but I would recommend that you check it in the textbook so that you can make use of it, inshallah, in your project if you want. So what is the idea of document expansion? So here we are not talking about re-ranking. Okay, so we will not introduce new methods for re-ranking, although the textbook has others. But for the course, we will not introduce any new methods for re-ranking, but we will introduce new method in that space, which is the pre-processing space. Okay, which we didn't talk about at all in almost at all in once we started to talk about neural ranking, but now we will, inshallah. So the focus of this part will be on pre-processing, and we want to talk about vocabulary mismatch. I think you heard this terminology before, right? What do you mean by vocabulary mismatch?
This word of the query term was not found in the vocabulary, or it's not included in the entire collection.
You are close, but here we are not talking about the query and the collection. We are talking about the query and
the document.
Document. Yes. Okay, so vocabulary mismatch here means that the query terms usually don't appear in the document, even if the document is relevant. Okay, or at least sometimes. Okay, so when that happens, that we call this vocabulary mismatch, because the vocabulary that was used in the query doesn't match the vocabulary that is used in the document. Okay. Type. With these neural methods, is this still a problem? First, why is that a problem? Of course, it is a problem because of the way that we use the standard retrieval models. The standard retrieval models does matching by exact match, right? The words here have to be here so that they match, right? So vocabulary mismatch was a big problem, because if the terms that are in the query don't appear in the document exactly as they appear in the query, then the match will not happen, or at least there will be partial match. Okay, so that's with exact match models like BM25 or language modeling or any bag of words model. Type. With neural ranking, is it still a problem? Because in neural ranking, we started to say, okay, we have embeddings. Embeddings capture meanings, and now even if the original words are not exactly the same, but if they are synonyms, then they should have similar embeddings, so they will match, and blah blah blah, right? We said that. With this, do we still have a problem of vocabulary mismatch? Will vocabulary mismatch makes any problem for us, or it's solved already? Alas, with the idea of contextual embeddings and all of that, it is solved.
The base retrieval is done by the BM25 or QLM, so they will retrieve on the basis of exact match.
Exactly. Thank you, Hera. So the basic retrieval step still depends on exact matching. Remember, the semantic matching is done based on the ranked list that we get initially from exact matching retrieval models. So we still have the problem. If the query terms didn't appear in the document, then the documents will not appear in the BM25 score ranked list, and thus BERT will not see it in the first place. So relevant text that has no overlap with query terms will not be retrieved and will never be re-ranked, of course. Type. Remember, we started to talk about expansion before, right? And we said that query expansion might be a solution to that. Do you remember what is query expansion? What was query expansion?
Yes, we
relevance. Yes.
Yes, Hira. Ahlam, go ahead.
It depends on the type of the expansion, if it's blind or explicit or implicit.
Yeah, but what is the idea of query expansion?
The idea that I will retrieve some documents and take the co-occurrence terms with the terms of the query and expand the query with these terms.
Very good. So the idea of query expansion is to expand the query with some terms that are related to the original terms, so that when we use now the expanded query, we'll get better results. Okay, at least we increase the recall and we might get better results. Okay, thanks, Ahlam. So that's the expansion that we talked about, which is query expansion. Now, it turns out that query expansion is not the only type of expansion. Okay, so we can also, so we know query expansion, we get a query and we pass a query to the query expansion module and we get expanded query out of it. But there is another type for expansion called document expansion. So in document expansion, we don't expand the query, we expand a document. So we take a document, okay, and we find out terms that are related to that document so that we can add to the document. Type. Why should we do that?
Excuse me, doctor.
Yes. Ahlam.
I think we did something like that with the mu or lambda, like adding terms to a document to
smoothing,
yes.
Right?
Yes.
Yes, but we didn't do that explicitly. Yani, we didn't say that we will expand the documents with related terms. Remember, in smoothing, we did it for all terms in the collection. It wasn't it wasn't for specific terms, so we didn't do any selection. It was just smoothing, just to include that any term in the collection can have non-zero probability to appear in the document. But it wasn't, first, it wasn't specific. We didn't say, yes, these terms are more related to the document, so we'll add them. Second, it was not explicit. We didn't add terms explicitly to the document. As you see here, as you will see very soon, when we say document expansion, we add terms to the document itself as if these terms appear in the original document before indexing, which means that we will index the new document with the newly added terms. So that's why I say explicit expansion. So we actually add these terms to the document, and we append them to the document as if they appear actually in the original document, and then we index the document. So this is different from what we did in smoothing, but good that you remember that we had something like this, but that's not exactly document expansion. Okay, so back to my question, why should we do something like document expansion? We understand query expansion. We want to add terms to the query so that we try to minimize the vocabulary mismatch problem, right? Why can we do also document expansion? What is the intuition? Will that do you think that it will also minimize or maybe avoid to some extent the vocabulary mismatch problem? Any ideas, any thoughts?
Doctor,
we have time till suhoor, right? Any thoughts? Abdullah?
Yes, Doctor. I believe it will, because if we add new terms to the document, then we are avoiding more of the mismatch between the query terms and the document.
Yes, so it's very similar to the idea of query expansion. Okay, we have two sides that have a mismatch, right? So you either expand the first or you expand the second. Okay, so we thought about expanding the query, but actually also the document can be expanded. In fact, to expand the query, we have little information about the topic, which is represented by the words in the query, which is much shorter than the document. So when we expand the query, we have few terms, right? And we use these few terms to add new terms. But for the document, we have lots of information. We have all the terms in the document, which is, of course, much larger than the query. So we know more about the context of the topic, much more than the query. So it is easier to find good terms when we do document expansion than query expansion, because we have much larger context here. We have the entire document, but for the query we have very short text, very few terms. Okay, type. Another difference between them: query expansion is done offline or online?
Online.
Online, of course, right? Right. How about document expansion?
It's offline.
Offline. Document expansion is query independent. So we can do it offline. We can do it in the pre-processing phase. We expand every document and then we index it. Okay. Right.
And Doctor, for this expansion, we will be using static embeddings,
we didn't talk about it yet, Hira. Stay tuned. Okay.
Okay.
Just two or three slides more. I think we'll talk about it. Next slide. Next two slides we will say how. Okay. Type. Doc2 query is one approach for document expansion. How do we do it in doc2query? The idea is, let's expand the document with predicted query terms. Yani, if you are given that document, this is the theoretical idea, okay? Not exactly how we do it. The theoretical idea. If you are given the document, guess what kind of query terms that you will use to retrieve that document for. And that will be a good candidate for expansion for the document. Okay? So that's the idea of document to query. It's like you want to translate the document into the query. That's why it's called doc to query. From the document,
so we will not do it for each.
Sorry?
Doctor, so we will not do it for each term in the document because it will too much.
Oh, no. We'll not do it for individual terms. We'll do it for the entire document. So given the document, we'll get the expanded, the new term or the terms that we want to expand the document with. Okay. So for that, the authors used the transformer, sequence to sequence transformer. So that's the original transformer, not BERT. So they used the transformer. Remember, the transformer actually was for sequence to sequence tasks, right? Like translation. Here it is similar. Given the document, I want to generate a query that is relevant, not relevant to that document, that for which this document is relevant, or to which this document is relevant. Okay, so you can think of it as translation. I want to translate the document into a query. So if you remember, that was the nice figure of the transformer. So this is the encoder part and this is the decoder part. So from the decoder part, I want to generate the query terms for a given document. So I will pass the document here and I want to get the query terms here. And that will be trained similar to the way that we talked about last week. But now the sentence or the two inputs that we talked about in the previous lecture in last week was English and French, right? Or French and English. Here it will be document and query. So from the relevant judgments, we have the document and we have the query and the documents that are relevant to it. So we just switch them. So we give the document and we want to predict the query to which this document is relevant.
So, Doctor, we will input the terms of the document.
Yes, relevant document and query will be the output. So when we train, we give both the relevant document and the query. We want to learn a model that afterwards in inference will get only the relevant document and will generate the query for it. Now this query will be appended to the document. Okay, so this query now will be like the terms that we should add to the document to expand it. Okay, is it clear, Ahlam?
Yes, I mean the input for the transformer is the terms of the document. Am I right?
For training?
Yes.
For inference. For training, you add both. You add the sentence, the document here, and the query here, as we discussed in the last week.
Mm-hmm.
But for inference, you only give okay, I will need to turn off the virtual background for some reason. I don't know why. Anyway, but for inference, you will use the relevant document only, and you will generate the query. You predict the query. Okay.
Oh, okay.
Okay. Right. So that's the main idea. Here's the input. Now, after we train the model, the doc2query model, the transformer, then we pass the document, we get the predicted query. Okay. Then we concatenate both. Now the new document will be this, the original one, concatenated with the with whatever generated as the query. Now this document will go to indexing. So all of this will be done before indexing. That's why we say that this is done in pre-processing. Okay, because we want to get new version for each document, new expanded document. Okay, now when we get a query, we use the new index to get hopefully better documents now. Is the idea now clear? Any question about the idea, about the approach? Hello, did I answer your question or not yet?
Yes, doctor.
Okay.
Thank you.
Any other questions? Okay. In practice, we don't get only one query. We can get more than one query. Okay. If you remember last time when we talked about training, when we talked about getting the query from the getting the translated passage from the transformer, we said that we always get the maximum, the term that with the maximum probability, right? And then we added back and then generate the next one. This will give us just one translation, right? But if I want to get multiple translations, I can sample from the top 5 or 10 words for each time step. Okay, if I sample randomly, I will get a new term, and then I will get different next term and so on. So I can generate multiple queries actually by sampling from the top K terms at each time step. So I can predict actually more than one query that way. And we add them eventually all to the document. Now let me show you quickly the results. Here we started with BM25 as usual. With doc2query, we got much better results. So this is 0.18 MRR, jump to 0.27. It's almost 10 points. Okay, in MRR, and in NDCG and on a different collection, we also got 14 points. There's no BERT here as for reranking, by the way. And we didn't even do reranking yet. Okay, this is just like first step. Remember, doc2query is pre-processing step. Okay, so we expand the document, then index, then do BM25 again, but on the expanded documents. So this is BM25 on the original documents. This is BM25 on the expanded documents after using doc2query. Okay, if we do that with relevance feedback, we get here we got a drop because of the problem, some problems in how the test collection is designed. But here we got a slight improvement over, as you see, over the expansion without relevance feedback. Now, if we use monobert over that, we get even additional improvement, of course. Okay, so you see here from 0.214 to 0.379. Okay, so starting from BM25, we got some improvements with document expansion that made improvement. Okay, that translated with improvement, with a big improvement, not big, 2 points improvement or 1.5 points improvement in performance over monobert using, or actually BM25 using the original documents plus monobert. Okay, so I want to make sure that you understand these numbers. This number compared with this number, what is the difference? Sorry, this number and this number.
This number 0.27 and 0.36, like using monobert.
0.18 and 0.36.
0.18 is BM25, using only in the initial, and here using the monobert with BM25.
Exactly. Okay, so no expansion here. Now compare between this one and this one. What is the difference? The difference here is that in both cases we used document expansion, but we added mono-BERT. Okay, but we added mono-BERT. So this is mono-BERT over the expanded. Now, if we want to only to see the effect of expansion over mono-BERT, compare between these two numbers. Okay, this number is BM25 plus mono-BERT. This number is BM25 plus mono-BERT, but BM25 applied on expanded documents. Okay, so we got a bit of improvement. I think between 1 point and 2 points. Type. Here is an example of expanded documents. You see here, this is the document and this is the predicted query. And whatever is highlighted here with green are terms that actually appear in the document, because the predicted query might have some words that appear already in the document, right? And it might have new ones. So over the queries in this experiment, 69% of the terms were copied. I mean, copied here means they appeared already in the original documents, and 31% didn't. So 31% were new terms, like weather here. And if you look at this document, you will not see the word weather, but actually we are talking about the weather. Hottest month and temperatures and coldest and so on. So weather appeared in the predicted query, but it was not actually in the original document. Okay, time. Here, I think we are very close. Sorry, Annie, I think we need maybe 5 more minutes. Here, we want to know which is the more important, is to get terms that already appear in the document or new terms. First, let me talk about this copied thing. If I just got terms that appear in the document, would that be any useful when we add them again to the document? Yani, the word here, the word Washington DC, these two words appeared in the query. Would it be beneficial just to add Washington DC only to that document? Yani, would it make any difference?
It will make difference, Doctor, with the term frequency.
Yes, exactly. So this is like boosting the weight of these terms, right? This is like saying, look, these terms are more important, so let's improve or increase their weight. Okay, so even if we got only old or existing terms, that will be beneficial, or might be beneficial at least. So this experiment shows that. Okay, so this is the performance. This is just BM25. Okay, just BM25. BM25 on the original document, we got this number. With expansion, but only with new words, yani we only added new words, we got that number, which is not much far from without any expansion. Now, if we add on the original document, if we add just the existing words, which is like boosting the weights of some terms, we got even higher boost than only adding new words. Okay. Now, if we add both, we get even higher, even much higher. Come in. Okay. So that means that both are useful and both are different. The doc2 query benefited in 2 different ways: improving or emphasizing the importance of some terms by repeating them, because the term frequency, as Abdullah said, the term frequency will increase, which means that the TF-IDF value, for example, will increase. And the new terms also are important, okay? Because without them, there was a big difference here. So you see here, even the improvement when we add both is more than the addition of the improvements from both the new words and the copied words, which is really nice. Yani that means that adding them together made interaction that or added much more than adding them individually. Okay, it's not just additive. And if you added the difference between this and that and this and that together, will not add to this. Okay, this really is even better than just adding the improvements together. Okay, so Dr. Query is really effective in this case. Now, this is very surprising. This is very interesting. In this experiment, we don't add, we don't expand the document. We replace the document with the expansion. Yani, for example, here, instead of this document, this whole document, we replace it just with the predicted query, whether in Washington, D.C. only. Okay, what happens? Replace it where? Remember, we changed the document completely. So the indexed document will be this one, not this one anymore. Much shorter, of course. What happens? The performance actually increases, not of course on this new line, but on the original one even. Okay, yani that means that the expanded query only better represents the document than the entire document itself. That's a very interesting result. So predicted queries are better than original documents. So this is like summarizing the document by very few words. And it's not just a compact form, it's even better representation because it gave us better results. Of course, this expansion alone was not better than the document plus the expansion, which is that line. Okay, so still we need both to get better performance, but this indicates that the predicted query is really very informative and even better representation than the entire document. Maybe we can have something in between these two lines that will be even better than that. We don't know. Yes, Maria.
So using only the predicting queries will save indexing, and it will later on in the mono-BERT and the BERT, it will be much smaller document. So
exactly.
I would need like
faster. Yes.
Faster, yes.
I'm not sure if the authors did this experiment or not. I don't know. Okay, maybe they did, maybe not. I don't know. But yes, it's really interesting to do it, to see the effect on the next step. Yani maybe mono BERT or duo BERT or whatever BERT variant will pick up this difference. So we don't need even to add the new document. Okay, that's an experiment that should be done. Type how to expand long documents. Remember, we use the transformer, right? For expansion. Dr. Query is a transformer-based expansion, which still has the same limitation of BERT. So if I have long document, what should I do? Chunk it, apply each chunk on Dr. Query, then get the terms for that, then add them all to the document. That's the most straightforward way. Okay, so just pass each chunk to Dr. Query, get terms, and then put all of them together, add all of them together with the document to index the new document. So that's the most straightforward way. Takeaways, messages of document expansion. The advantages: documents have more context. We said that, so we have much more information. So it should be an easy prediction task than the query expansion. Documents can be processed offline, so the time needed is not very critical because we are not doing it online, and we can do that in parallel because we can do that on every document in parallel. The disadvantages: we have to iterate over the entire collection. Although it is offline, but if we have billion document collection, it will take time. Okay, although it's offline, but it needs time and of course computing power, because we have to go through the entire collection. Also, with longer documents, remember that we are expanding the document, right? So the documents will be longer. That means that query processing also will be a bit slower because the posting lists will be longer, right? So with the posting lists longer, then of course the query will take more time to get the ranked list or the scored lists. Okay, so that's the disadvantage of document expansion. With that, we are done. Any question on document expansion? So the idea is clear?
Yes.
Any questions? I know that we are, it is really interesting. I think this is the latest time I have ever taught a lecture at since I started teaching. I have never stopped lecture at 11 p.m. before, but that's Ramadan, and Ramadan is 11 p.m. actually is early in Ramadan. So I'm not, I don't feel very embarrassed of doing that. And it's the last lecture, so I think it deserves it because it's the topics that we talked about today is really the state of the art. Kind of, and this is maybe 2020. 2021, we might have some new models, but you are very close to the state of the art in IR, really. So I think it deserves this time. We even didn't talk about so many other things. I wish we had 2 more lectures, the one that we missed because of the sports day, and the one that we missed because of the early exam week, the week that was taken from the semester for the exams. With these 2 weeks, we would have discussed more topics from that survey, but I think that's okay. That's enough for you, and I hope that you will have now time to spend on the projects. Any questions on today's topic?
No, Doctor, we would like to thank you. Thank you so much for it's very interesting topic in general, IR. We really had fun and it's challenging. You keep thinking all the time. Every time there's something new, you have to learn. So thank you so much for everything.
You're welcome. You're welcome, Mary. Really, this is my specialty, so I always enjoy teaching it. It's really my pleasure to teach this course. And the lectures, actually, I enjoyed the lectures also with you. Being in class is a lot of fun. Any instructor didn't actually notice or realize that until we switched to online teaching. Alhamdulillah that we had most of the lectures, maybe 90% of the lectures in class, so we had this nice interaction. As you said, it was really also fun to me. Not only to you. I hope that you really enjoyed all of the topics. I personally enjoyed that specific course very much. Thank you all for your nice questions and discussions. I hope that the conclusion of the course also will be nice and fun, and also inshallah very useful in terms of learning, inshallah, for the projects. So I'm really looking forward to the projects. I hope that you will spend this next couple of weeks working hard on the project so that the conclusion of the course, inshallah, will be something that we all happy with. Any last comment about the
Doctor, we can send you the feedback for you, or just do the survey and that's it?
Of course, you should do the online survey. But if you want also to send me any feedback, I will be very happy to get it. But of course, anything that will be sent to me will not be the official feedback, will be just the informal feedback. I would be really happy if you send me your feedback, if you will. But of course, you have to do it also in the official survey. So doing both will be great.
Yes, thank you, Doctor.
Okay, you're welcome. Any feedback, by the way, will be very good. But just remember that to be constructive. give feedback that will make the course positive. Be fair. Tell what you liked and what you didn't like. Not just one side. And if whenever you send me also positive and negative comments. I will, inshallah, if I teach the course again, then for sure I benefit a lot from the feedback. Many of the comments that I got from the last version of the course I already included this time, so I try always to adapt to the feedback that I get. Sorry for keeping you that late, but I hope that you benefited a lot from the course, you enjoyed it, and inshallah, good luck. Best of not, I don't like luck, but best of inshallah effort and success in the projects, inshallah. Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh.
Thank you, Doctor. Wish to see you again in another courses.
I hope so. Inshallah. Inshallah, I will be happy to see you again.
جزاك الله خير.
يلا كل عام وانت بخير دكتور. كل عام بخير. دكتور
صحة وسلامة.
السلام عليكم. شكرا دكتور. الله يعطيك العافية.
الله يعافيك. وعليكم السلام.
دكتور كلاس. مع السلامة.
وعليكم السلام.